and everything? Hello?
Yes, we can.
Oh, perfect. Thank you very much. So, hello everyone. My name is Ariadna Murguia-Berthier, and I'll be talking about HARM3D plus NUC, which is a topic that Scott already kind of mentioned, but I'll just do it in a little bit more detail, and I'll tell you all about the TCAN collaboration, which I'm sure you all heard because Manuela's there, so you'll hear more about the results. So I think I'll go quite fast with the introduction, but of course, if you have any questions, just let me know. Everyone knows that GW Sentinel 817 happened, and what we know is that we had two neutron stars that were orbiting around each other. Before the merger, there were some tidal tails, there were expulsion of matter, and you see this on round debris. You also then get a hypermassive neutron star as the remnant, which might or might not collapse into a black hole. This is all surrounded by an accretion disk. So in particular, we can have one of two results depending on the mass of this hypermassive neutron star. So it can either collapse into a black hole or it just can be stable for a little while longer. And it depends on whether the mass of the remnant is larger than the mass at which cell gravitating objects collapse, or if it's less than that. So in the case in particular of GW Sentinel 817, we know that it should not have been just a direct collapse into a black hole. It should have stayed a hypermassive neutron star for at least several milliseconds, several hundreds of milliseconds in particular. And then once we have this hypermassive neutron star, it's going to be differentially rotating. It's going to be very hot. It's going to then go into uniform rotation. And as it does so, we have another different threshold mass. So we can have one of two different results now. We can either have a delayed collapse to a black hole or a stable magnetar, again, depending on the mass. Due to some energetic arguments, we have reasons to believe that GW Sentinel 817 comes from a delayed collapse to a black hole. So basically, we have that the two neutron stars orbit around each other. They create this hypermassive neutron star that after, like, say, a second or so, it collapses into a black hole. So we need to be able to model that. And all of this surrounded by an accretion disk. Now, what's going to happen is that material from the accretion disk is going to be transported onto the black hole. And there's going to be a relativistic jet launched, which is a gamma ray burst, and that is what we saw in GW Sentinel 817. Now, a very important emission, I mean, there's the gamma rays, there's also the non-thermal emission, but another very important emission is the thermal emission from GW Sentinel 817. It is important, first of all, because that's actually the reason why we discovered the electromagnetic counterpart. So we actually saw first the thermal emission. And you can clearly see this discovery image. Here you see nothing. And then here you see the kilonova, or the thermal emission, which is really cute. And so basically, at that point, every telescope on Earth was pointed at it. And we saw a lot of the electromagnetic signature. Now, this is unlike anything we've ever seen before. So first it was very, very, very blue, but then at some point it just became red really, really fast. And this was unlike any other transient we have ever known. So we need to be able to model that, and we need to be able to say what happened. So we know that the thermal emission should come from our process elements being created, be it from several winds. It could be also from the accretion disk. There's tons of different mechanisms which can create our process elements. But the main idea is that these other process elements are going to be homologously expanding. At some point, they are going to cool, they're going to become stable, and they're going to emit. So that is the thermal emission that we see. It's just the radioactive emission from the R process elements. So of course, then we need to be able to say where these R process elements were created and how much. In particular, that is to tell our observer friends when and where to look. So this is here, I'm just showing the light curve of GW Sentinel 817. This is a kilonova emission, which you probably all seen. And yeah, we need to be able to model that. So in the focus of this talk and in the focus of our research, I'm going to focus more on several accretion disk winds or accretion disk outflows that could be one of the main creators of these R process elements. So we need to figure out exactly how much. So let me just talk a little bit about the physics in the accretion disk. So again, in the case of GW Sentinel 817, the end result is going to be a black hole surrounded by an accretion. Now, this accretion disk is going to be very hot and also very dense. Actually, photons are going to be trapped all over, so we don't care about the photons. We care a lot. So the main cooling agent is not going to be the photons. It's actually going to be the neutrinos. So in the outer edges of the disk, we're going to have lots of alpha particles. These alpha particles are going to create some alpha-driven wind, which is going to also be important in the modeling of this accretion disk. At some point, these alpha particles are going to recombine, and that is going to release, well, if you're going from alpha to free nucleons and protons, it's going to dissociate, and it's going to release energy through this wind. Then at some point, at some igneous radius, we're going to create neutrinos. We're going to create both electron antineutrinos and neutrinos, and that is going to be the main cooling agent until at some point, we're going to become opaque to both the neutrino and the antineutrino. So all of that needs to be modeled in order to fully understand what happens during the merger. Now, there are several neutrino reactions. The ones that I'm going to be focusing more is this charge beta process, and well, there are some others, but this charge beta process is the main neutrino creation mechanisms. And as you can see, I mean, not surprising, if you have a neutron star merger, we're going to have a lot of neutrons. So this reaction right here is going to be the most dominant one. Therefore, we're going to create more electron antineutrinos than electron neutrinos. Now, the opacity source, on the other hand, is going to just be the inverse of the charge beta process. And we can see that since we have lots of neutrons, again, this reaction is going to be the most dominant one. Therefore, the neutrinos are going to be the main absorption source. So just like as a summary of all that I've told you so far, this is the radius. Here I'm plotting mass accretion rate and the radius of our disk, and let's see what happens. So again, in the outer edges, we have some alpha particles that then start to recombine into, dissociate into free nucleons and protons. At some point, we're going to create neutrinos, which are the main cooling agent. And then we're going to become opaque first to the neutrinos and then to the antineutrinos, just due to these reactions. So all of that needs to be modeled. So basically, we need some realistic equation of state that can correctly model this dissociation from alpha particles to free nucleons. And we also need some kind of neutrino transport in order to fully understand how the disk gets thinner and what happens. So in the case of HARM3D, just a little spoiler alert, this is going to be done through a leakage scheme. Now, again, this is all very, very important because we need to understand what elements are formed in the disk. There is a high debate as whether we have lanthanides or we don't have lanthanides in the disk. And this is very important because lanthanides have very high opacities. And if they have very high opacities, that means that the thermal emission from the lanthanides is going to be red, and it's going to peak later. So if we have lanthanides, we're going to have a different emission than if we don't. So we need to be able to figure out whether or not we have lanthanides in order to tell our observer friends when, and particularly in what bands, to look for these kilonova emissions when all these amazing telescopes are online. So our simulations were done on HARM3D. I mean, I put a slide on this, but you all heard Scott's amazing talk, so I'm not going to go into any details. Again, like new to this version, I think you mentioned we evolved the electron fraction. We have a realistic equation of state, and we also have a neutrino lipid scheme. So let me briefly discuss the TCAN collaboration and what our aim is and what we're trying to do. So the goal is to do the most realistic simulations possible from the neutron star mergers when they're separate from each other, 45 kilometers apart, to the post-merger. So we want to be able to follow the entire outflow in order to do the nucleosynthesis. So we're using Lorraine as the initial data to get the two binary neutron stars. We then evolved this with Illinois GRMHD and SPRITZ, which has numerical relativity, as I'm sure a lot of people have talked about. And then we do this handoff procedure, which is a very new and cool thing, where we interpolate the metric, the magnetic fields, everything into HARM3D, and then we use this as initial conditions. The advantage, of course, is that, first of all, this numerical relativity codes are Cartesian, so therefore you have lots of diffusion. Even though they have adaptive mesh refinement, you still have lots of diffusion, and their domain, it has to be very small because you're doing all this really cool evolution. Whereas in HARM, we actually have a very, very big domain where we can follow the outflow for like a second, which is a lot. And also, as Scott mentioned, in HARM3D, we have this new grids, which have much less diffusion. So that's what we want to do. Now, again, for more information, I mean, you have Manuela right there in the conference, so you can ask her. She's a big leader. So this is what we're trying to do. My part in particular is in the post-merger phase and in the HARM3D case. So what I did was, this is all already done and published, and hopefully, as Scott mentioned, it will be publicly available. So I put a tabulated equation of state in HARM3D and a neutrino leakage scheme in HARM3D. So in particular, for the tabulated equation of state, we do this interpolation of tables. And what's nice about this is that it naturally takes care of this alpha-driven wind. The neutrino leakage scheme it's a simple well, not simple. It's an approximation of the transport, and we basically just add source terms to the energy and the number equation. Now, the interpolation in particular, it's where it actually matters the most is in this conservative primitive variable solver. We also get it to get the sound speed, but the main part where we actually had to modify the code was in this conservative primitive solver. So I can go into as much detail as anyone wants. This, I think, would be the place to do it. But what we did was we have now five different solvers, and we have all these different routines. So the main idea is that we want to solve these two different equations, and you can see Scott's paper for a lot more details. And here we have this just conserved variables and this independent variables. So, I mean, we have two independent variables, we have two equations, we can just solve it, right? In particular, the equation of state interpolation comes in when we're trying to do this modified enthalpy, let's call it, this W or this modified enthalpy and the pressure. So we needed to just change the code so that we could interpolate all the different quantities here. And now this is one of our routines. We have another different, which is this same 2D method, but plus a safe guess. And you can check out this paper if you want. There's also this 2D method, but we actually use a dogleg method in order to solve the equations. And it allows for a more robust convergence. A different routine that we added was this 3D method that was made by Dan Siegel and also in Cerda Duran. And in here, instead of having two equations to variables, we have three independent variables, three different equations. So these are the three different equations, and here we have the three variables. And again, the equation of state comes in when we're trying to get the modified enthalpy, the pressure, and of course the energy. There's also a different routine, which is called the Palenzuela routine. Here we have one equation and one independent variable. And this one is the most robust one. So we added several conserved variable routines, and this is our result. So we did all these 5 different routines, and here I'm just showing the relative error for a certain density and a certain temperature. So we just put this as our primitives. We turned them to conserved variables. We used our solver to go from the conserved variables to the primitive variables, and then we calculated this relative error. So what you can very clearly see right away, oh, by the way, there's like little dots. I don't know if you can see them. I hope you can see my mouse because I'm just pointing at this little like white dots. This means that there was no solution found. So as you can clearly see from this plot, the 3D method is actually the one with the least error. It's also the fastest method, but it's the least robust one. It was the one that had the highest failures. Then the 2D method is better in that sense. It's slower, but it's a little bit more robust. The Palenzuela routine was very robust. So what we do is now we have this solver. So we go first to the 3D solver. If it fails, it goes to the 2D. If it fails, it goes to the other 2Ds, et cetera, et cetera. So we try to do the 3D one first, and then it goes to all the other methods. So that is what we added for the equation of state. And as you can see, it very clearly works. So we're happy about that. Now, as for the leakage scheme, these are just the reactions that I showed before. These are the reactions that were considered. This is all an analytical scheme. And it's mainly based on this really cool paper by Rufford et al. What we do is we add a cooling rate in the energy equation, and we add an emission rate in the number equation. These different rates are just the interpolation between the optically thick and optically thin regime, and we use factorially averaged quantities. So if we are in the opaque region, it just naturally goes to the diffusion, And if we're in the transparent region, we actually consider all this opacities for the absorption and the scattering of these different reactions that I showed before. And then we just do this kind of interpolation. So all of this is done. And another thing is we need to calculate the optical depth. So it actually comes in the calculation of this diffusion timescale, so this TDiff. And what we do for the optical depth is, instead of doing a global approach, what we do for the calculation is a local approach. So we use this method by Nielsen et al., which just tries to get the minimum of the optical depth to each of the neighbors, plus just some, this is just a kappa ds. And it gets the minimum of, it takes basically this quantity for each of the neighbors, and it tries to do the minimum, and then it does lots of iterations. So basically what this is saying is that, imagine if we're in a cell, we're trying to say, oh, what's the most optimal path for the neutrino to get out? And we're trying to build a path for the neutrino to get out. So if we do one of these minimums, we're saying, okay, go to this cell, because this cell is the one with the least, with the path of least resistance. If we do another iteration, we're saying the next cell to that one, et cetera, et cetera. So once we do the entire domain, we can trace the path for the neutrino to go out. So that is what we do. And again, and how we tested it was with a sphere of constant density and constant temperature. So here in the pink, I'm just showing the optical depth as a function of the radius of a sphere that, again, constant density and constant temperature. This is the analytical one, the pink one. And the other ones, the other plots are what's the optical depth for a certain number of iterations. So if you do one iteration, we actually do a pretty bad job. But if we do a lot of iterations, the more iterations of this quantity that we do, we approach the real analytical optical depth. So we created a convergence criterion that you can check out in our paper. And we actually do a pretty good job of just doing it analytically. So if you see this dashed line is the analytical solution, and our simulations all do a pretty good job independent of the resolution. So that's great. And it only also comes in the diffusion timescale. So so just again, like as a reminder, it comes in here. We also tested this leakage scheme. So what we do was just evolve this isotropic, optically thin, constant density gas. And if you do this, the equations for the evolution equations are just going to be, reduced to these two different equations. And you can semi-analytically solve them, and you can also do just a simulation. And we found out that we do a pretty good job of estimating both the electron fraction and the evolution of the temperature. So that is great. We now have a leakage scheme. We have the equation of state. So let's just do some science with it. So this is all in our paper, in the HARM3D plus NUC paper. So what we did was we evolved the disk. This is just a magnetized accretion disk. We have an isentropic disk. It's a Fishbone-Moncrief disk with a poloidal magnetic field, and it has a realistic equation of strain and neutrino cooling. Here I'm showing the electron fraction, and here I'm showing the density. So if I press play, you can see that here we have this alpha-driven wind. So in these regions, we have the recombination from free nucleons and protons to alpha particles. So we have this wind. And we also have that the neutrinos are going to act mainly in this part of the disk, and they are going to thin the disk. Another really cool thing that you can see is that throughout an entire simulation, the disk remained quite neutron rich, which is just something that Dan Siegel also found, and it's because this disk is self-regulating. So the heating due to the MHD stresses is going to be equilibrated with the neutrino cooling. So we're going to see that the electron fraction remains really low in these regions, which is great. Now I'm just going to show this exact same movie, but just in a larger domain. You might, if you squint your eyes, you might see that the disk is right here. So I'll just press play and you'll see why I wanted this high domain. So as you can see, we have this really, really large outflow of really neutron-rich material that's going at very high speeds. And that is what we want to simulate in the TCAN collaboration. So just for completion, here I'm just showing that this thickness is a function of radius and the average m dot is a function of radius. in these regions right here, from 100 to like 300 kilometers, we see that the alpha wind is where it's dominating, and we can also see it from the average m dot, where here positive means that it's being accreted, negative means that it's a wind. So in these regions, we see a very powerful wind, which is the alpha-driven wind, whereas in the innermost regions, we see accretion. And we see that the disk is going to get thinner, and it's going to get thinner just due to the neutrino cooling. So the alpha wind and the neutrinos are acting in different parts of the disk, and we can clearly see it from here. Also, for completion, I'm showing here the luminosity of the neutrino luminosity and the mass accretion rate. And as we can see, after some time, it clearly follows the mass accretion rate, which is kind of what we expected, because the neutrinos are going to be created just due to the heating of the material as it enters the black hole. So all of that is great. And now I'll show you some results from the TCAN collaboration. So here I'm just, let me see if I can press pause. So here I'm going to show a movie of what we're trying to do. Again, just as a reminder, the TCAN collaboration wants to do the simulations from when the neutron stars are orbiting around each other to the post-merger itself. And we do it in Illinois GRMHD, and then we hand it off onto HARM3D. What I'm going to show right now is a movie of these two neutron stars that are orbiting around each other, and then how it's being handed on onto HARM. You can see Fede's paper if you want to learn more about the handoff, what kind of interpolations for the metric, the magnetic field we do, et cetera, because he did a pretty good job of measuring all the quantities. So here, the simulation is in Illinois GRMHD. Here are the two neutron stars. So we have numerical relativity, adaptive mesh refinement, and Cartesian grid. So you can just see the neutron stars orbiting around each other, pretty cute. And then at some point, it's going to change into the HARM3D grid, and we're going to basically see basically no difference in the density, which is exactly what we want. So here we have our grid, and then it passes on to HARM3D. So that was, and then we evolved this in HARM3D with a much, much larger domain. Now we can also see the same movie, but instead in a different view. Now they're orbiting like towards the screen. And you can see also, I zoom out, and then it's going to be passed on onto HARM3D. And you'll see no difference in the density, but you'll see the different bits. So great, we now have the tools. So our friends from Illinois GRMHD gave us some simulations. We did also the handoff. And I'm also going to redirect to Joseph's paper. This is how it looks in the Illinois GRMHD side. So here we have the two neutron stars that are orbiting around each other. And then we have we have here the electron fraction. Here's the interface between the two neutron stars. We have this dynamical ejecta. And you can check out this really cool paper by Joseph where we analyze, mainly he analyzes where do the main particles come from the bound ejecta, which is something that a lot of people have analyzed. So I'm just going to publicize his paper. It's a really cool paper. And let me just show you so now that we have the Illinois GRMHD simulations, let's evolve them in HARM. So let's see, okay. So here I'm just going to show different quantities. Here's the density, here's the electron fraction, and here's the sigma, which is v squared over rho. This is for the simulation. It has already been handed off. So time 0 in HARM3D means a certain time in the handoff. So I'm just going to press play. And you can see that this gets thinner. You can also see that it's still very neutron rich. And I guess I can evolve it. It gets interesting a little bit later, but I want to talk more about different modes about different things that we're seeing. And here are the same things. So here's the density, and here's the electron fraction for that same simulation. It's the same, but it's just at, you can see a larger domain. It's zoomed out, and you can actually see very clearly the results from the Illinois GRMHD simulation. So here are the results of their electron fraction. And you can see this is all evolved so consistently. We have not seen jets, which is something that we need to discuss at some point with the collaboration. And I don't know if I'll let it run a little bit more. We have done the simulations up to like 200 milliseconds so far, and we see these outflows, but we're not sure if they're real or numerical. So just some preliminary results. Again, this is all that I've shown is very preliminary. We're still discussing, working on everything. So here I'm just showing the magnetic energy as a function of time. In yellow, I'm showing the toroidal component, and in this like pinkish, we can see the perpendicular component, which is the poloidal component, and the total magnetic energy. So we still haven't seen an increase in the perpendicular component. Some toroidal should go into the perpendicular component. We're still thinking about that. Here I'm just showing the neutrino luminosity. And here I'm showing that this thickness as a function, well, that this thickness averaged between certain times. So another cool thing that we have done is we analyzed the mass accretion rate of the bound matter and the unbound matter. Here I want you to notice that the scales are very, very different. I had to change the scale so that you can actually see the unbound matter being accreted. This is being accreted at 2 Rg, which is almost near the ISCO. And here is just the mass accretion rate as a function of radius averaged between several times. So one thing that you can see is that you see this also in here. Positive means that it's going inward, negative means that it's going outward. So you can clearly see that after certain times, we start to see this outflow, that's outgoing of bound matter. And in here, we also see this large outflow. Another really cool thing that we have been discussing about is we have seen the formation of an m=1 mode. So this, instead of it being a non-bagel code, because I always get equatorial and meridional confused. So if we looked at it as a non-bagel cut, those would be the movies that I showed you. So here we're looking at a bagel cut. So we actually cut the disk like this. We're seeing it from up. And I'm going to show the movie. And what I want you to focus on is that you very clearly see the creation of an m=1 mode around 20 milliseconds. So let me press play. So it might be a little bit too fast, but I'll pause it right here. You very clearly see that we have this m=1 mode. And Scott did this analysis of the power of the m=1 mode. And just like, let me show you this figure right here. We can very clearly see, well, the movie, we can very clearly see the m=1 mode after. And we can also analyze it, and it's very clear. So if you look at the ratio of the power of the m=1 mode versus the m=0 mode, this is just, this is the ratio, this is the radio, and this is the time. So if we look at it going up, we actually see the development of the mode, and this is just at what radius does it matter. So if we start to look at it, we see that around like 40 milliseconds, we see this very powerful m=1 mode being created, and it's extending up until like 30 kilometers. So we're still, and you can also see at larger times that we see this lump that's also moving a lot of different matter. We are still not 100% sure that this is real, but we're starting to think that this is more physical than numerical. So we can discuss about that. But I have a feeling that it is physical, and we're waiting on some Illinois geometry simulations to tell us that it's more of a real thing, and not of another result of the interpolation of the metric or some other sort of numerical engineering. So basically, the conclusions is that HARM3D plus NUC is, I don't know if the newest, but one version of HARM3D. It has a neutrino leakage scheme and a tabulated equation of state. We are doing and analyzing simulations of binary neutron stars with a handoff procedure, where the post-merger phase has neutrino cooling or in an approximate manner, and initial conditions from numerical relativity code. And in the future, we're going to be doing the nucleosynthesis. And also I'll redirect you to Joseph Senari's paper to see some analysis with the tracer particles in Illinois geometry. So thank you very much. And if you have any questions, just please let me know.
Hi, I had one question about the movie on the M=1 mode. What were you plotting in that video? Kind of in the upper right-hand corner. What was
Let me.
going on there?
You mean this one?
Yes.
Yeah. So this is the same movie that I showed before of the density. It's just a movie of the times, and
Okay.
this is the bagel cut. So yeah, it's just a movie, and here, if I pause it, you can very clearly see this M=1 mode. And if we evolve it more in time, you also see this lump being created and moving. I mean, it's just moving around,
Okay.
dragging matter. Yeah.
Great. Thank you.
Of course.
I come up to the mic. So.
Have you measured the angular or looked at the angular momentum profile in the disk?
I don't think so yet. No.
Okay.
No, we're still analyzing all of this.
Because that looks like the Papalousi-Pringle instability, right? So
Yeah, that's what I've heard. So that's one of the things that I'm trying. Yeah,
right.
yeah, I've heard about that.
Fallout with radius.
Yeah.
Yeah, it's pretty comparing. It's pretty comparing. Okay.
Does your space-time retain? You check if your space-time after you import it has a net linear momentum?
No. Yeah.
So that's what we're trying to figure out. So Scott did some simulations where we phi averaged the metric, and we still see this M=1 mode. So we don't think it comes from the metric interpolation. So what we're waiting on right now is the Illinois GRMHD team is following the simulations up to like 30 milliseconds in post handoff. And we're trying to see if they also develop the M=1 mode, because if they do, then that means that it's physical.
Any other questions?
Yeah. So yeah, very intriguing stuff. In binary neutron star mergers, when you're left with a neutron star remnant, you clearly see this M=1 mode. You can see this in Hydra simulations. We also see them in like MHD simulations. But the understanding there is that you have the remnant, and is actually the remnant that is powering this mode, right? And I think there are some simulations by David Radice that basically, when the system collapsed into a black hole, they don't see this anymore. But maybe it takes some time to develop. Maybe this is something different.
Yeah. I mean that's why we're trying to see if it's physical, because also this is for equal. I should have mentioned this is for an equal mass binary, so we should not have a kick.
Yeah. So one question: do you see outflows from this, basically generated by this? Do you have spiral waves from the disk, and that are correlated with the outflows of the disk?
So I mean, the spiral waves are most likely the ones driving accretion in this case, which is, or at least so I talked to Julian a little bit, and I don't know, is Julian there?
No.
No. Too bad. Okay, so he was saying, this is all again preliminary, like analysis is still being done, that the Reynolds stresses due to this M=1 mode might be higher than the magnetic stresses. So it might be the case, and again, preliminary, that this M=1 mode is actually the one driving accretion. So it should be correlated with the outflows, but we're still in the process of thinking about if that is something that's real.
Yeah, we also have evidence of that, but having the remnant, the neutron star remnant there, not the black hole, so it's different. Yeah.
You have to check if the density waves get non-linear. while the density wave is linear, it can travel through the disk, and if it's non-linear, will actually steepen, drive shocks, and then the viscosity of that transport angle. It looked like it was close to YE where you were the low Y into this. So
I can let you the movie again.
I think people are discussing, but I don't think you can hear, right?
No.
Okay, any other questions for the speaker? And then maybe,
Also, Scott's there, so if you have any more questions, like feel free to ask Scott. He's also like doing this amazing work.
okay, well, thank you. Let's thank the speaker one more time.
Thank you. Have a really nice day. Bye.